Hello everyone, welcome to David Griffiths Electrodynamics. This is problem 3.35. So I'm going to go over the problem statement here. We have a solid sphere of radius capital R centered at the origin. The northern hemisphere carries a uniform charge density rho naught, and the southern hemisphere carries a uniform charge density minus rho naught. So they're equal but opposite charged. We want to find the approximate electric field, E of r theta, for points far from the sphere, where little r, right, is the variable to our point, and then where r is much, much greater than the radius of the sphere. So essentially, when we're much, much further from the sphere, this thing's probably going to look like a point charge. And we can use like a, I think we can basically use a multipole expansion to figure out what the approximate electric field would be. And we're just going to do the first two terms of the multipole expansion. So we're going to look at the monopole term and the dipole term. So let's look at this. So we have this sphere here with the charge rho naught on the top half and a charge minus rho naught on the bottom half. So the total charge of the net charge of our sphere, right, is just rho naught minus rho naught, or zero, right? The total net charge is just zero. Now it's not distributed equally, but it's still symmetric, and the total charge added up is zero. So our monopole potential, which depends on the total charge, Q, well, zero is going to be on the numerator, so that just makes our monopole term zero. So we will have no monopole term. But we will have a dipole term, and I wrote down the expression for the potential of the dipole term here. So it's 1 over 4 pi epsilon naught p dot r hat, where p is the dipole moment, divided by r squared. And then I wrote down the integral expression for the dipole moment here. So it's this integral over the volume d tau of r prime, rho of r prime, where r prime is like a vector to the charge. Each little piece of charge, and then rho is the charge density function. Now, due to the spherical symmetry of this problem, if you go to any point of charge on this sphere, and you consider like a dipole moment due to that, it should be canceled out from an equally symmetric point of charge on the other half of the sphere in a similar location. And, well, at least all the horizontal components should be canceling out. So just by symmetry, the dipole moments of all the charges on the sphere should just be have only vertical components. So really the dipole moment should be just along the z-axis. And that's just kind of a symmetry argument. I'm not going to do a rigorous proof of that, but typically in physics, you use a lot of arguments from symmetry, so you kind of have to get used to that. So our dipole moment expression is going to be this integral over the volume, and our charge density is going to be, we have to do two integrals, right? We're going to do an integral over the top half and an integral of the minus of the bottom half, because they have different, they're slightly different in terms of their charge density. So we're going to do two different integrals. So the top half, the r prime, it's going to be this vector along the z-axis, because we can kind of just assume that all the charge is along the z-axis because everything kind of cancels out horizontally. So our r prime for the integration is going to be z, and then our charge density function is just rho naught, that's constant, and then d tau, which we'll plug in later, and then z hat is the direction because this is a vector, and then we have a minus z hat, and so the minus sign here comes from the minus z hat because the bottom half, the dipole moment, is going to be pointing in the opposite direction. And then we have a minus rho naught for the charge density, d tau, so that's going to end up making this a plus. So these two integrals are going to be the exact same, so then it's going to be 0 naught d tau z hat plus z rho naught d tau z hat. So that's just going to be twice of the same integral. So we can just we can add a 2 out front, and then the bounds for each integral will be slightly different, because like the bottom half we'd be integrating from pi over 2 to pi, versus the top half is integrating from 0 to pi over 2 for theta. But that gets sort of handled by just combining the two integrals as well. So you could do it either way. It'll all get situated out mathematically no matter which way you do it. I'm just going to combine the two integrals and just integrate from 0 to pi over 2, but we're effectively doing that twice. But the minus signs from the difference in bounds also just get accounted for because of the minus signs due to the unit vectors and whatnot. So it's all kind of handled. So we have 2 rho naught. Those are just constants. Then this volume integral, right? This is really a volume integral, d tau. So our R integral will go from 0 to capital R, or the radius of the sphere. Our theta integral we're just going to do from 0 to pi over 2, but we're effectively doing that twice. So we are capturing the entire sphere in a way. And then our phi integral is going to go from 0 to pi, 2 pi, so all the way around. And then z, we can express this in terms of theta as just r cosine of theta in spherical coordinates. And I put a prime here on the r's to denote the difference between the integration bounds here. So that's r prime cosine theta, and then d tau in spherical coordinates, right? This is a differential volume element. That's just r prime squared, or r squared sine of theta dr d theta d phi. So I just plugged in that, and now we have to do this integral. So the easiest one here is the phi integral. Nothing depends on phi except for d phi. So that's just going to be phi when you do that integral. And when you plug in 0 to 2 pi, you get 2 pi. So I just go ahead and do that integral and pull the 2 pi out. So we have 4 pi rho naught. Then we have the integral from r equals 0 to r of r cubed to dr. And then the theta integral from 0 to pi over 2 is cosine theta sine of theta d theta. So doing the r integral, this just gives us r to the 4th over 4. And plugging in the bounds, you just get the capital R to the 4th. And that's a constant. So I pull that out of the integral. And the only remaining integral is the one with respect to theta. And you can do this integral via u substitution. So if you let u be sine of theta, then du is just cosine of theta d theta. And that gives you an integral with respect to u, where the bounds change from 0 to 1 instead of 0 to pi over 2. Because when sine of theta is, when theta is 0, u is 0. When sine is pi over 2, or when theta is pi over 2, then that means u is 1, because sine of pi over 2 is 1. So our bounds change from 0 to 1, and then our integral just becomes u to u, which is a very easy integral. You just get u squared over 2. So our total term here is pi rho naught r to the 4th, capital R to the 4th, u squared over 2 from 0 to 1. And then that just becomes pi rho naught r to the 4th over 2 when you plug in those bounds for u. And then we have our z hat vector here. So this becomes our dipole moment, which we need. This isn't the answer to the problem. This is just the dipole moment of our configuration, which we need to calculate the electric field. Right, so our electric field is given by this for a dipole. So we can just plug in the magnitude of our dipole moment here. So we get pi rho naught r to the 4th divided by 8 pi epsilon naught r cubed, because the 2 on the bottom here makes that an 8. And then we get our 2 cosine theta r hat plus our sine of theta theta hat. And this is, I guess I should write this as like electric field of a dipole. Because really, for if you're very far away from this spherically symmetric sphere, it's just going to look like a point charge, or like it's basically going to look like a pure dipole at distances very, very far away. So that's why we can kind of use this approximation of saying that, you know, we can kind of use this dipole electric field term. The only thing we had to figure out was what is the potential. Well, we had to figure out what is the dipole moment of our configuration to be able to use this expression. So anyways, I hope that makes it clear. I think you could also use this dipole term and use the monopole and dipole terms of the potential, and then like add those together and take the derivative of it and stuff to get the electric field, and you should get the same expression essentially. There's two ways, but I just went ahead and just like used the fact that we know what this is. So the hard part was just getting the dipole moment. So anyways, if you guys enjoyed this video, feel free to leave a like, comment, subscribe if you haven't already. If you want to support me and my channel and what I'm doing, you can do that via the Buy Me a Coffee link down below, or use the Patreon link. You can get access to these written solutions as well if you want those. All right, that about sums it up, and I will see you all on the next video.